Good morning. Welcome to Krishna's classroom. We continue with our discussions on Lebesgue integration theory. Last time, what we worked on was getting approximations in the sense of outer measure for M star measurable sets and by what are called open sets and say F sigma and G delta sets. So what we have proved is that the measurable subset, or what you call M star measurable subset of the real line, is in fact nearly equal to a F sigma set and a G delta set. A G delta set is the approximation from outside and F sigma is an approximation from inside, but they have the same measure. I mean M star, that is outer measure. Okay. Now what we are going to prove is the following. Suppose we have a M star measurable set with finite outer measure, then we show that it is nearly equal to the disjoint union of finite number of open sets. So that's our, we shall now a M star measurable subset of R with finite M star measure, outer measure, is nearly equal the disjoint union of open, a disjoint union of finite number of finitely many open intervals. So the assumptions are the set is having a finite outer measure, and then we prove that it is nearly equal to in the sense that this can be approximated by a collection of finite number of open intervals which are disjoint. Okay, so let us take the theorem. That means M star measurement. let m star of finite, then for every epsilon positive there exists a finite disjoint collection of open intervals there are two things here, finite and disjoint open intervals. k running from 1 to n for some n for which O is, it's an open set defined as K and m star of is less than it. Here we are not saying that the open set is inside the measurable set or outside the measurable set. It's something like this. See, this is your E. I am using Venn diagram again, and then you have some collection of open intervals. This is what you call the O. And then what it says is that the outer measure of this portion plus the outer measure of this portion. So this is actually E O slash E. This is E. This is O slash E. This is, of course, E slash. So that m star of this plus m star of this is less than epsilon. That is roughly the error that you make. Okay. Now let us prove this result. This is Venn diagram because on R it is difficult to draw diagrams. So by the first part of the approximation theorem, discussed above in the last lecture, there exists an open set U such that E is contained in U and M star of U slash E is less than epsilon rate. So that such a set exists. Now we make use of the following fact. Now every open set of real numbers is a disjoint union of countable collection of open intervals. Disjoint collection of open intervals. It's a countable collection. Countable collection of a disjoint union of a countable collection of open intervals. That is, U is equal to now we know that each ik is measurable, is M star measurable, is in the script M. Okay, and M star of is equal to length of hence for every n sigma k equal to 1 to n length of ik is equal to M star of union k equal to 1 to n ik, and this is less than or equal to M star of star, and this is fine. Okay, right? Therefore, what we do now is this: take this such that this is less than epsilon. Therefore, what you have is, what you have shown is that this sum is bounded for each n. Okay, what does it mean? Now choose a natural number. Epsilon positive n for which sigma n plus 1 to infinity of L of by k is less than small. Choose this. That is possible because of this relation. You know that this is finite, therefore that is true. So we define now this is the definition of O. And this n is the n that we have chosen here. Okay, so this particular n. That is what you have as your n. So now we try to prove this estimates. Okay, now define this is true. So we have defined it. Now you see that O slash is contained in U slash. Okay, because O is by monotonicity m star, you have m star of O slash less than or equal to m star of U slash which is less than 7. Okay, so that we have chosen earlier. Now what more? Further, U is therefore E slash O is contained in U slash O, and that's equal to infinity L of ik, and you know that m star of E slash O is less than or equal to sigma k equal to n plus 1 to infinity length of ik, and that is less than epsilon by. Now, so you have two relations now. One is this one. This inequality. The other one is this inequality. Now, put them together. This implies together you have m star of So that completes the proof. Okay. Now we make some remark. Here we have assumed that E is measurable, M star measurable, and having a finite M star measure. Now we look at any bounded set E. So what we can say is at EB, a bounded and we are not assuming that E belongs to do not assume for any epsilon positive, there exists an open set O such that E is O and M star of O is less than okay, so this is that. This estimate is there. Here we are not assuming E is an M star measurable set. Okay. Of course, this does not imply because by the excision property is equal to is false if it is not M star. So this is the crucial point. Because you cannot say this. You had this. He is, say, M star measurable. This is okay. Right. That completes nearly the approximations that we have. Now it is time we drop this M star measurable terminology and then start giving this class a new name which we shall use henceforth. So let us go to the title of this, namely Measurable. So this is what we want to define now. It's a crucial definition. All the work that we have done so far is towards getting this out. That's what we have done so far. See, we introduced the notion of what is called outer measure. This is done for any subset of R, okay, which is linked to the concept of length, or which essentially generalizes the concept of length. Then we introduce a notion called M star measurability. So we isolated a class of sets from it, which are called M star measurable. I mean, the significance of this will be clear the moment we start about talking about non-measurable sets. Okay, and such collection we gave a name and we called it M star measurable sets. And this M star measurable sets have a very nice structure. You see that it's a sigma algebra. Secondly, it has got the property that it is translation invariant, and all the intervals belong to this class. And for intervals, the M star measure or the M star outer measure of intervals is essentially the length of the interval, so that it goes to, or what we have done so far really gears to what our objective is. That means generalizing the concept of length for arbitrary subsets of, if possible, arbitrary subsets of. Now you see that we have already seen that this collection is very rich. This collection is very rich in the sense that it contains all the intervals. Okay, it contains all the open sets. It contains all the closed sets. The whole of R is in it, and the empty set is in it, and they are all translation invariant. Okay, so all this nice structure that you have for this M star measurable collection. Okay, so still we are not sure whether it covers the whole thing, but we explored it further in the approximation theorems and said that it is nearly equal to, in the sense of M star measure, M star outer measure, a F sigma set or a G delta set, or you see the entire class of Borel sets. Borel set is the smallest sigma algebra that contains all the open sets, so that the topology of the real line, the sets which constitute the topology of the real line, is now in this collection. Okay, and that's a big thing, as we are going to see later when we start defining what are called the measurable functions. So at that time I will make some more remarks about this. So it's a very rich class that we have got, and we are still not very sure whether it covers the entire class of subsets. So let us keep it as it is, and later we shall make some remarks about it. So we define the restriction of, so we take, see, M star M is, we call the definition, this is the collection of all this is the collection that we are talking. Okay. Now we give a name. Any set is called a Lebesgue measurable set. So all sets of script M are called Lebesgue. Okay. So M star restricted to M. So the set function M star restricted to M that means the outer measure on elements of M is called the Lebesgue measure. Sure. And M of E, the measure of is given by so this is what we call the Lebesgue measure. So M script M is called a collection of all Lebesgue measurable sets, and the outer measure of any Lebesgue measurable set is what we call the Lebesgue measure. Okay. So henceforth we will be using M for Lebesgue measure and script M for the collection of Lebesgue measurable sets. Because the Lebesgue measurable sets is a rich collection containing all Borel sets. And this is what is called the Lebesgue measure. So we have crafted what is called the length of a an arbitrary set possibly, but not for all. So further remark is that we have generalized the concept of length for all measurable sets. M, which is a natural extension of the Kozhikode. For the intervals. Now this is what you have. So you have M of I. This is the extension, and we have M of what you call E plus so it is translation in it. Okay. And then of course M is countably additive, that we have proved, and all Borel sets belong to this class, and that's what. So I think we have got to a stage where what we had been looking for, and now we can comfortably start talking about the length of, or in inverted commas, the length of a huge class of subsets of R, which probably serve our purpose for integrating what are called some more weird functions than the Riemann integrable functions. Now this is our objective, to go beyond Riemann integrable functions. And this is the foundation for introducing the Lebesgue. With this remark, we stop now. We will further look at the properties of this particular class. Okay, thank you very much. It's a short lecture.